All malicious code falls into one of two operational categories based on how it executes: programs that must attach to an existing file and programs that run entirely on their own. A true virus is strictly parasitic. It requires a legitimate executable host file to function, and it relies on a user running that infected file to replicate. This map details the global spread of the WannaCry attack, illustrating a threat that operates differently. This is a worm. It self-propagates autonomously by scanning for and exploiting network vulnerabilities, moving across borders without any human intervention. Trojans, by contrast, rely entirely on human deception. The malicious functionality is hidden inside an application that appears useful, tricking the target into executing the payload manually. Once execution occurs, some malware seeks deep persistence. Rootkits establish control at the operating system's kernel or boot level. From that privileged position, they intercept system calls to effectively render their files and active processes invisible to the infected machine. The functionality of a payload is distinct from how it actually reaches the target memory space. Delivery mechanisms fall into two distinct architectures: droppers and downloaders. A dropper acts as a self-contained carrier. The primary malicious executable is embedded directly within its own resource sections. Once launched, it extracts and runs the payload locally, requiring zero outbound network traffic. A downloader is structured as a lightweight first stage. Its only job is to reach out to a remote command and control server and fetch the actual payload. Because of this architectural requirement, it is highly vulnerable to network isolation tactics. Misidentifying these operational behaviors during a live incident leads an analyst to deploy the wrong containment playbook. Blocking a file hash will not stop a self-propagating worm, and ignoring a downloader's remote domain guarantees the payload will still arrive. Facing a newly discovered, uncatalogued zero-day binary requires extracting logic from the noise. Analysts use a three-question diagnostic framework to safely strip away the chaos. Question 1. How did it arrive? Establishing the entry vector, whether it was an emailed macro, an infected USB drive, or a compromised software update, defines the perimeter of the breach. Question 2. What does it do? The analyst must map the core execution behavior, determining if the ultimate goal is rapid file encryption, silent keystroke surveillance, or bulk data exfiltration. Question 3. How does it hide? The binary will attempt to evade the analyst's observation, most commonly through aggressive code packing or by injecting its payload into legitimate system memory. Some modern variants execute this evasion by neso-dropping a recognizable file at all. These living-off-the-land binaries abuse native OS administrative tools, like PowerShell, to run malicious scripts directly in memory. By systematically answering these three questions, the analyst constructs the minimum operational logic needed to classify the threat and formulate an effective technical response. To pull those answers from a hostile file, investigators rely on two distinct observation methodologies: static and dynamic analysis. Static analysis involves examining the file structure, metadata, strings, and raw assembly instructions, strictly without executing the binary. It is entirely safe. The technique has a severe physical limitation. If the author compresses or encrypts the core executable, a technique known as packing, the static analyst is blinded, reading only scrambled data instead of instructions. The countermeasure is dynamic analysis. The analyst detonates the file inside an isolated virtual machine, monitoring exactly which files it writes, which registry keys it alters, and which IP addresses it contacts. Yet dynamic analysis only reveals what the code chooses to do in that specific moment. If the payload requires a precise command line argument to run, or waits for a time delay trigger, the malicious execution path remains dormant and invisible to the sandbox. Malware authors physically alter their code to exploit these blind spots. Polymorphic malware generates a completely unique decryption envelope for every single infection. The underlying payload is identical, but the file hash changes entirely, rendering static signature databases useless. Metamorphism goes further. Instead of just wrapping the code in a new decryptor, a metamorphic engine aggressively rewrites the logical instruction structure itself. It swaps equivalent commands, reorders blocks, and inserts dead code. The resulting binary looks entirely different to a static scanner, while performing the exact same tasks. To detect it, an analyst must ignore byte patterns and search the executable for deeper mathematical anomalies. The most reliable method to detect an obfuscated payload without executing it relies on Shannon entropy, a mathematical measurement of data randomness and disorder. The entropy scale is plotted along a strict logarithmic boundary, starting at 0 and ending at 8.0. Standard, unencrypted x86 compiled code contains predictable structures and repeated opcodes. Consequently, legitimate executables predictably generate an entropy score hovering between 5.0 and 6.5. When data is heavily compressed or encrypted, those predictable structures are destroyed. The file contents behave mathematically like pure randomness, forcing the entropy measurement sharply above the 7.0 threshold. This line graph plots the entropy levels across thousands of data blocks in a known malicious executable's code section. The wide plateau, situated squarely between the 4.8 and 5.4 marks, represents the malware's standard unencrypted structural code. The sharp, isolated spike jumping near the end of the file is a severe mathematical anomaly. Analysis of that specific block reveals heavily encrypted configuration data, hiding the domain of the attacker's command and control server. Recognizing an abrupt entropy spike inside a code section gives the analyst immediate proof that the file is actively concealing functionality, without requiring a dangerous detonation in memory. Obfuscation techniques only protect the file while it is inactive on disk. To achieve its goal, the malware must eventually unpack itself, enter system memory, and execute according to the CPU's fixed architecture rules. The CPU handles this execution logic using registers, high-speed storage locations located directly on the processor. The most active of these is the EAX register. EAX acts as the primary accumulator. It performs constant arithmetic operations and, by architectural design, almost invariably stores the final return values of executed functions. The most critical execution marker is the EIP, or instruction pointer. The EIP holds the exact memory address of the very next instruction the CPU is scheduled to process. As the processor executes instructions, it requires short-term volatile memory to manage function calls and parameters. This is handled by a data structure called the stack. The stack grows and shrinks dynamically. The ESP, or stack pointer register, functions as a sliding marker that constantly tracks the absolute top of the current active stack frame. To prevent the CPU from losing track of local variables as the stack shifts, the architecture uses the EBP, the base pointer. The EBP locks in as a static, reliable anchor for the duration of a function call. Analysts read the specific memory offsets from the EBP anchor to locate hidden decryption keys. More importantly, by manipulating the address stored inside the EIP instruction pointer, the analyst dictates exactly what the malicious process is allowed to do next. To safely inspect those registers and dump unpacked memory, analysts use debuggers to forcibly freeze the malware mid-execution. They accomplish this by setting breakpoints. When placing a software breakpoint, the debugger overwrites the first byte of the target instruction with the opcode 0xCC. When the execution path hits that byte, it triggers a system interrupt. The active process pauses entirely, handing control to the analyst. Self-defending malware anticipates this tactic. Advanced variants will actively scan their own running memory space, searching for anomalous 0xCC bytes to determine if an analyst is monitoring them. When malware detects and evades software breakpoints, the analyst must deploy a lower-level countermeasure, hardware breakpoints. Hardware breakpoints do not alter a single byte of memory. They are implemented directly at the processor level, utilizing the x86 architecture's internal debug registers, designated DR0 through DR3. Because the hardware breakpoint operates on the silicon, rather than modifying the executable's code, it perfectly bypasses the malware's internal integrity checks. The code cannot detect it is being watched. The technique has a rigid physical limitation. Because there are only 4 specific debug registers built into the architecture, analysts can set exactly 4 concurrent hardware breakpoints per active thread. The process of analyzing malware operates as a deterministic hierarchy. From mapping the high-level taxonomy of a threat, to tracking entropy spikes, down to utilizing silicon registers to trap a malicious process,
analysts systematically strip away layers of evasion until the core logic is exposed and defeated.